sense. Otherwise, I'll draw it again if you want. I'm moving some value into register 4 for now. So these registers, R3, R4, you can think of them as like temporary variables. That's stored within the CPU. And then this store byte instruction is saying, I want to store my value in R4 into the address that R3 is pointing to with a 0 offset. So the 0 comes from here. 0 offset. So that means I'm storing a value of FF into register address of 0x40000. Yes, you need to do a load back. Register 4. I'll answer your question later, Emily, if that's okay. I'll answer MD's question first. So these registers here are registers that are temporary within your CPU simulator. So these registers, don't get confused with the memory registers that you're allocating in Verilog. Yeah.
Are you pointing at something we can't see?
I'm drawing on the screen.
We can't see the drawing that you just did.
Pardon?
The drawing of the registers. I can't see what you're pointing at.
This one?
Yeah, I can't see anything.
You can't see it? No. What am I showing? No wonder everyone's confused. Where is my sharing screen is paused. Is that better?
Yep.
Sorry. I must have accidentally pressed pause sharing. So let me erase. Did you get quarters up, Horace?
Yes, I have it ready.
Okay. I'll let you take over after. Is that all right? So these are the temporary registers I was talking about, MD. R4 is here, just stored in the CPU. R3 holds the address that I want to store to. Does that make sense, MD? I'm looking at the chat. There's quite a few people coming in. Does that make sense? Cool. I'm going to change the instructions a bit so that we can I can show you guys how to check for maybe half word in a byte load. So just to quickly answer Emily's question, you can load a byte. Let's load half word from the memory address into R5 to R3. So this is getting value at R3, put it into R5. The Zoom doesn't have a problem. For some reason, there's a waiting room. And I thought we turned off the waiting room already. Let me just double check. Sorry. Horace, can you check out the waiting room?
Yeah, I'll check that.
Okay, Kasav asks, what does a 0 in store half word or load word means? This 0 is your offset to the address. So if it's a 0, that means I offset a 0 to here, which means nothing. Let's say if I do 1 R3, you point to 4000, 4002. That's right, yeah, Horace? Just want to confirm.
What was that, Alex?
With a 1 offset, it points to this one, right?
No. The offset of 1 is always a byte offset.
Just a byte. So that means it's
4001.
for the other one. Yeah. My apologies. I think it'd be better to show you guys in action anyway. So this will make a lot more sense. So I'm loading a byte from R3, and then I'm loading a byte from an offset of R3. Okay. So this part will make a lot more sense, I think. So right now I'm storing a byte into R6 from R3 with a 0 offset, and I want to see what the difference is with R7 and 1 byte offset. Right now I'm storing 0xCCFF, so let's see what that does. Compile and load. Sorry. It didn't compile properly. Well, I must have typed an error somewhere.
Aaron, it's I think that's out of the range of a 16-bit signed value. If you use
the sign, yeah.
Yeah.
Okay. Something more simple.
You can try the unsigned version.
It's okay. Okay. So I'm just gonna step over. So right now I store the half word. I store the half word here. So we just quickly check the memory address. So it's what I stored, 0C0F. So I've changed it a bit. Now we see what doing the load half word does into R5. So I do another single step. So I've loaded whatever is in the address of R3 into R5 for the half word. And if I check here, R5 has whatever R4 was in terms of the half word. So these 4 bytes. Then we look at what load byte means with 0 offset and what load byte means with 1 offset. So let's see. If I do another single step and then another single step. So this is kind of replicating what you guys did in part 1. So for R6, you only look at the lower byte of the half word. So you only look at the 0F here, which means 0F for register 6 with a 0 offset. Whereas with a 1 byte offset here, for R7, you're looking at the upper one. So you're looking at these two, this byte, sorry. And then you're loading a 0C into R7 instead. So that's how you can check your different cases. I think that should answer what Emily said. Does that answer your question, Emily? Is there anything else I should cover, Horace, while we're waiting?
I'm not sure. Did you mention that accessing the memory is sort of a simulation of accessing the slave device?
Yeah. I don't know if they understood that though.
So the slave device is a memory map device, which means the range of addresses that are assigned to an external bus bridge. It would be similar to the accessing a memory device that is assigned to that same address space. So in the simulator on CPU later, there is a 16 megabyte memory setup, if Aaron just scrolls down. So there's pre-allocated memory of 16 megabytes. That is assigned to the address space that would equal 16 megabytes on the Avalon bus. And so you accessing that memory with those addresses would be similar to what you would have done if you had. Sorry, is my audio not good?
It's a bit echoey, I guess.
Okay, anyway, so accessing that would be similar to accessing the external bus bridge with the same address.
We gotta bring out the lab sheet so it's a bit easier. Lab sheet, this one. Yeah. Do you want to draw on my screen, Horace?
What am I doing?
Do you want? Pardon?
What did you want me to explain?
Just showing how it's related to the lab.
Oh, okay.
Is it clear? How do you want?
I think it might be pretty clear too. Okay, so this device at the moment is connected to the bus bridge. And it's assigned addresses.
Yeah, I think your mic got a bit worse. I'll let you sort out the mic first. So you just want me to explain that the slave peripheral has all your memory mapped addresses, right?
Yeah.
Yeah, that's all right. I'll take over. So what Horace is saying is, in your CPU later, I'll open it up again. Keep the tabs next to each other. It makes it easier. You can pre-allocate space. So just try to recall in the first part of the lab, you allocated 512 kilobytes of memory, I believe, to your external bus bridge. And this, even though there's no 512 kilobytes here for the pre-allocated memory, you can kind of imagine it. So in here would be a 512k bytes. Then you have your slave peripheral will be split into 4 chunks of memory. You can think of it as. So at the start, like I said before, is 0 times x0000, which is for reg 0. The second chunk starts at this memory map because we have 19 bits. So your 18th bit will be high, which means it'll be number 2. And then 0x4. Oh, sorry. That's not register. Register 1. And so on. So that's how it links to your simulation. Any other questions with that? How the simulation, how the CPU later, is related to the assembly code, which is related to the slave peripheral. Yell out on your mics or use the chat. We'll do breakout rooms soon. How does this apply to part 2? Are we just writing to a single register? So part 2, there's some key differences. Maybe I go through part 2 first and then I'll answer your question, Jonathan, if that's okay. So part 2 uses an SRAM, slightly different to what it used in part 1. I'm going to make a copy of this so we can get a side-by-side comparison. I'm not used to. Yeah. So this is part 1 on the right, and this is part 2 on the left. Hopefully it's not confusing. So there's some key differences in terms of the control signals for part 2. The first one that's really a bit different is that SRAM addresses are 18 bits. So you have to address it slightly differently to your 19 bits here. Your clock enable, all these ends on the right means it is active low. So to assert the signal high, you have to pull the signal low. So that's what active low is. So these are all active low. So it's slightly different to the slave peripheral because most of them are active high except for the right. This one is active low. All the chip definitions are here. So you have a separate control signal. Sorry, I'm just going to emit some. Oh, cool, thanks. So you have a separate control signal for your write enable and your read enable. So over here, compared to this, where it's only one signal, so that's one key difference. The other key difference is you have 2 bits to represent, 2 separate control signals to represent the upper and lower bytes that you're writing, whereas this one is just one control signal with 2 bits. That shouldn't make too much of a difference. Your write data has its own, correct me if I'm wrong, Horace. Your write data for the SRAM has its own data bus, but your DQ is shared with your read operations from the SRAM chip, so your read data, and then your write operations too. So, what did you say, Horace? Okay, so the DQ line is a shared line between the read and the write. So in the Quartus code, which I don't have on me, sorry, if you scroll down to the SRAM controller.v file, you see that some signals has to be asserted as a high impedance. That's what it is referring to. So your DQ is shared, so it has to be high impedance to see which if your controller or the SRAM chip is using that DQ line.
Hey, Aaron, can you hear me?
Yep, that's clearer.
Okay. I missed some of what you said because it cut out. But what I wanted to say was the SRAM write data that is shown in the lab sheet.
Then I draw.
Yeah.
Yep. This is part 1. This is part 2.
So this one here is actually the write data coming from the processor. And then you need to use that value and put it onto the SRAM DQ bus, which goes out to the SRAM chip. Yep, that's all I wanted to add.
Yep. So Jonathan's question was, how does the assembly code apply to SRAM? So for part 2, are we just writing to a single register? Do you want to answer that?
Oh, for me? Okay.
Yeah.
No, the assembly. So when you run an assembly instruction on the processor, that is going to generate all of the signals on this bus. And now your slave device is actually the SRAM controller. So that controller is going to talk in between. So if you imagine that this is your SRAM controller, that is then going to interface with the SRAM chip. Okay, so the SRAM chip has at least 512K locations. I think it's more than that, but we're only using 512K out of that. So every byte address should have a corresponding byte in that chip that you'll be accessing. Does that make sense?
Jonathan, does that answer your question?
Yeah, it's the same concept, but to SRAM instead of the peripheral device. The 7 segment is just used purely to display what was on your in your peripheral device registers. Which you can't really do with the SRAM because there are too many addresses to show on the 7 segment. Could I repeat again? Okay. Can you full screen the right side, please?
The right side? Sure.
Yeah.
Well, my mouse disappeared. There we go. Is that better?
Okay. So what I was saying before was, let's say you do a store byte in the processor. Executing that instruction will cause the processor to generate all of these signals on the bus. Okay. And now for part 2, the device on the bus is not the slave peripheral, it's the SRAM controller. Okay. The SRAM controller translates these signals into signals that are specific to the SRAM chip, and it communicates with the SRAM chip directly. So before, in your slave peripheral, your 4 registers existed in this slave peripheral device, but now the addresses or locations that you're writing to are in this physical SRAM chip. And the SRAM controller is translating these signals in order for you to be able to access the SRAM chip locations.
Where's my chat? There it is.
Does that make sense, MD?
Jonathan, did that part make sense as well? Because you asked the question before. Horace, should we continue with the quarters frequently asked questions, or should we just jump into breakout rooms now?
We can jump into breakout rooms. Mean to help individuals, or
yeah,
yeah, we could do that. Acknowledge. Okay.
I'll clear screen.
Sorry?
I'll clear the drawing.
Yeah, thanks. Okay, the acknowledge signal. By the way, is there any echo from my audio?
A little bit. I think it's more audible now to hear you. I mean,
Okay, let me try and turn down my.
in a test.
Yes. Okay. Right. The acknowledge signal is used purely to indicate to the processor that the slave device has completed its operation. So it needs to set the acknowledge value high for only one clock cycle. So only one of these pos edges should see the acknowledge high for one particular transaction on the bus. If you have two back-to-back transactions, then it would be on for an extra clock cycle. One transaction would be up to 16 bits because the bus size is 16 bits for this particular lab. So you're either transferring 1 byte or 2 bytes. And then when the slave is done, it will assert this acknowledge. Does that make sense? Are there any follow-up questions to that? Because I'm sure people are not completely getting that.
You guys prefer breakout rooms or questions? Oh, wait, Jonathan actually messaged. He says, yeah, just wondering why we no longer refer to the 4 registers for the SRAM. Sorry, I missed that. Horace?
Sorry, can you repeat that, Aaron?
For Jonathan, he asked about the SRAM. So he asked why we no longer refer to the 4 registers. It's because we don't have, there's too much range within the SRAM chip, right?
Yeah. Let me. Can you see my whiteboard?
Yeah.
Okay. So for part 1, we have this.
Let's just check. Turn off my mic.
Okay, so for part 1, we have this. The NEOS connects through the Avalon bus through to the peripheral. And in the peripheral, we only have 4 16-bit registers. Okay, so in that, Okay, there's nothing important there. In that, you can choose one of those 4 registers to then display on the 7-segment display. Now, for the second part, instead of the peripheral, you've got an SRAM chip outside. So if I change the color. So for part 2, you've got this SRAM chip, which is also off the FPGA chip. It is going to have 512 kilobytes of storage space or locations that you can write to. So for part 2, we remove this part. We'll get to the 7-segment part later, but for now, we go to this SRAM controller because the bus that's used for the SRAM chip is different. So this is the SRAM bus. And this is the SRAM controller. So the job of the SRAM controller is to convert from this bus language to that bus language, and then report back the other way as well. So because there are 512 kilobytes of locations, you can't easily pass that through to here to display. You'd have to use 19 different switches. So if you really wanted to, you could have 19 different switches to multiplex and then eventually show the value. But we don't do that. We just use, or we would have used the monitor program to test it in the labs or check the values. I think that covers it. What are the follow-up questions now? I can't hear you, Aaron.
Oh, sorry, I forgot to unmute.
What were you saying?
Rookie mistake. Hao Dong, hopefully I said that right. He wants us to go through the quarters facts. So I think it'd be good for you to share your screen for us for the quarters.
For the pieces?
Yep. So just like the common mistakes. Because I don't have it on here, sorry.
Yeah.
If anyone wants me to go into another breakout room now, I'm happy to do so. So just leave a message in the chat. Since this part might not be relevant for everyone.
Okay. The first thing that we should probably go through is the mistakes made with adding components in QSYS. So I've just got this open. I haven't set it up completely yet. So the first thing that we need to add is a NEOS processor. I can't remember which one we're using, but let's go with the standard edition.
Not the standard one, right?
So
I don't think we use the standard one. It says to not use the one with the multiply divide.
Is that what the lab says? So economy then?
Yeah.
Okay, so not the point I was trying to explain, but anyway. So once you've added that, then you make sure you make your connections to clock reset. And you probably need this to be connected to, whoops, not that one. Yeah. Okay, then you want to add a memory on-chip memory, which will store your instructions. Then you would connect that up also to clock and reset, and both the data master and the instruction master, because both you'll be storing both instructions and some data on this device. And then reset also to the JTAG because you want the JTAG to be able to control it, to reset it. Now, the bus bridge is here under the university program. So if you don't find it here, then you haven't installed the university program yet. So you can add that. We needed to choose an address range of 512 kilobytes and the data width of 16. Okay, and then that would also connect up to clock reset. This one is the debug reset. Did we connect the master to here as well? I can't remember that step. Aaron? Oh, he's known this. Never mind. Okay.
You don't have to. Yeah.
Yeah. Okay, so the next bit is what most people miss out, which is exporting this conduit. So the conduit is the actual interface here that's currently internal to the QSys, outside of the QSys component or your setup. So if you double click here, you can then give it a name. So some people tend to name this differently to then what was in the lab sheet. So if I just remove that, once you set this up, if you, let's first go and add the reset vector and exception vector, which would be your on-chip memory. So we get rid of those errors. And then we can also do why does this not come up with?
What's wrong?
It's not coming up with a base address.
Oh.
Oh, I think I added the wrong one.
Yeah,
Okay, so we need Avalon to external bus bridge. So don't make that mistake. Let's try to look different. Okay, this is better. Clock reset, and now both, sorry, just the data master. And you can add the JTAG as a reset as well. Okay, so if we lock this base address to 0 and then we assign base addresses, now we'll get rid of most of our errors. We also need to put in an interrupt request connection. And now there's this one warning left that is talking about this external interface must be exported or connected to a matching conduit. So that's what it's referring to, exporting of this. So if we don't export it, but we go to this HDL example tab, you see that the current ports that are exposed to the outside are just clock and reset. So to fix that, you have to export this and you have to give it the appropriate name. So bridge is the correct name. And now if we go back here, we see that all the bridge ports are also available to the outside of this module. If you were to name it something else, so if we update it to bridges 2, then you should see that the HDL example will change and it will use that name at the beginning. So if you have any errors about there is no port names called whatever you're trying to connect to, then that is the reason why.
Horace, can I get host? Or can you send me to a breakout room?
Just a second.
Yeah. Just with Jonathan.
Made you host.
Thanks. Oh, sorry to cut you off.
That's all right. Okay. So yeah, so that's one of the main problems that people tend to, the mistakes people tend to make. The other thing that we should note is that when you save this, you should choose a name that is the same as what is in the template that we provided you for the lab. If you don't choose the same name, then you have to update the template. So in the template, it is called neos_system. So once you save that as neos_system, you should see that the provided instantiation template that it gives you matches that. So neos system, and then it has all your ports. So then after generating this, so you would generate on this tab, then you can go back to Quartus, and in the top level, make sure that this name matches what you had in your QSys file. Make sure that you've added the QIP file. That's a mistake some people tend to make as well. Well, I haven't generated. Let's generate that. So when you generate, there will be a QIP file that's generated, which basically has the links to all the files that are required when Quartus compiles, needs to compile the QSys system, the QSys module, which is neos system. Okay. So we go to add or remove files. Now we'll search. What are we looking for? Here. So in your main project folder, in my case, it's called Buscom Lab. Under the named folder neos system in synthesis, what you will need to do here is change to all files, and that will give you the .qip file. So make sure you click add, otherwise it doesn't get added to the list. And then, yeah, so now it should be here. And if you were to compile this, it will be able to find the neos system. So sometimes some of you have compiled and the error is undefined entity, and whatever the name, it will say undefined entity neos system, and you've saved your QSys file as some other name, and that's why I can't find it. Or you've forgotten to add the .qip file here, and that's another reason. What other problems? In the test benches, okay, so in the test benches, make sure that you're using / and not \. I know that a lot of you have gone into Windows Explorer and copied the path in, and Windows Explorer will report the path with \. So make sure you're using /. Make sure the path is a full absolute path to the file that you're using, and make sure it's correct. And then that will avoid you having any issues later on. Aaron, is there anything else that you can think of? Can't hear you.
I only just returned.
So I just went through the QSys problems, and now I just pointed out
Cool.
/.
Let me think. There was a problem yesterday.
Does anyone have any issues that they face or they want to ask, or maybe I can answer right now?
I think you can talk about the top arrow for compilation is always compilation, not RTL simulation.
Yes. So when you're switching over to the test bench, you want to make sure that you switch over to RTL simulation. You want to make sure that you don't click this. This one will stop the full compilation. So run it from here by double clicking on analysis and elaboration and then RTL simulation. To make sure that you've set up the model sim correctly, there are two things that you need to do. The first thing is going to tools, options, and EDA tool options, and making sure that you've set this path correctly. Okay, so that path will be wherever your Altera folder is that you've installed under 13.0, Service Pack 1, Model Sim, and then this folder called Win32, ALOEM.
And the forward slash at the end.
Okay. No, don't worry, that forward slash didn't make
Doesn't matter, I guess.
But you do need to use forward slashes in that path, but Aaron was just referring to the very last. Oh no, okay, it works with backslashes for this as well. But yeah, he was referring to whether we needed this backslash at the end, which seems like you do. The second thing you need to set up was in settings under simulation, under EDA tool settings. Make sure you choose Model Sim Altera. Was this the thing that you were saying that you don't need, Aaron?
When people are trying to compile the actual project, you can't set the Model Sim Altera, otherwise it complains that you're using the web edition.
Okay, all right, so if you're doing a full compilation, is it full compilation or both with RTL as well?
Full compilation only.
Yeah, so when you're doing a full compilation, make sure you set this to none, but with RTL, you need to choose Model Sim Altera, maybe choose Verilog here, and this would be none. I'm currently using the custom view.vo. I think I explained that in the video. If you want to set up an automated startup for your Model Sim, but yeah, just make sure you choose Model Sim Altera and then Verilog, and then apply. Yeah, anything else?
I think that covers most of the discussion forum questions.
Mm-hmm.
So there were a few people yesterday asking me to explain like assembly code. So if you guys have those questions as well, maybe I can set up a breakout group just for you guys if you want to learn how all the assembly code works in more detail. Or we can just go for individual questions as well right now, since we covered what we wanted to cover for today.